Something is awry in our understanding of the universe. Cosmology seems to be heading for a showdown on one of its most basic questions. How fast is the universe expanding? For more than a decade, two types of measurements have been in disagreement. Observations of the current universe typically find the rate of expansion, called the Hubble constant, to be about 9% faster than predictions based on early universe data. Researchers hoped that James Webb, the most advanced telescope ever built, would help to settle the question once and for all. But consensus has so far failed to materialize. Instead, the Supreme Observatory has cemented the discrepancy with stunningly precise new observations that threaten to upend the standard model of cosmology. The new physics needed to modify or even replace the 40-year-old theory is now a topic of debate. An exciting and interesting possibility is that there's something we don't understand about the universe. Join us as we dig deep into how new ultra-deep images from James Webb just confirmed there is something seriously wrong with our understanding of the universe. Our universe started with a bang, the Big Bang. Energy, mass, and space flashed into existence all within a fleeting instant. Then, the young cosmos was formed. An expanding roiling plasma broth of matter and antimatter particles that popped into existence only to annihilate each other upon contact. Left to their own devices, the matter and antimatter inside this plasma should have consumed each other entirely, but scientists believe that some unknown imbalance enabled more matter than antimatter to be produced, saving the universe from immediate self-destruction. Gravity compressed the plasma pockets, squeezing and heating the matter so that sound waves traveling just over half the speed of light, called baryon acoustic oscillations, rippled across their surface. Meanwhile, the high energy density of the early universe's crowded contents stretched spacetime, pulling a small fraction of this matter safely from the fray. As the universe inflated like a balloon, the standard story goes that ordinary matter, which interacts with light, congealed around clumps of invisible dark matter to create the first galaxies connected together by a vast cosmic web. Initially, as the universe's contents spread out, its energy density, and therefore its expansion rate, decreased. But then, roughly 5 billion years ago, galaxies began to recede once more at an ever faster rate. The cause was another invisible and mysterious entity known as dark energy. The simplest and most popular explanation for dark energy is that it is a cosmological constant, an inflationary energy that is the same everywhere and at every moment, woven into the stretching fabric of spacetime. Added together, the energy densities of ordinary matter, dark energy, and energy from light set the upper speed limit of the universe's expansion. They are also key ingredients in the lambda-cold dark matter or lambda-CDM model of cosmology, which maps the growth of the cosmos and predicts its end, with matter eventually spread so thin it experiences a heat death called the Big Freeze. Many of the model's predictions have been proven to be highly accurate. But here's where the problems begin. Despite much searching, astronomers have no clue what dark matter or dark energy are. As Ofer Lahav, a professor of astronomy at University College London involved in galaxy surveys of dark energy, said, "Most people agree that the universe's present composition is 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing fact is we don't understand the last two of them. But an even greater threat to the lambda-CDM model has materialized. Depending on what method astrophysicists use, the universe appears to be growing at different rates, a disparity known as the Hubble tension. Methods that peer into the early universe show it expanding significantly faster than lambda-CDM predicts. Those methods have been vetted and verified by countless observations. Therefore, as Nobel Prize-winning astrophysicist Adam Rees, who led the team that made the new James Webb measurement, said, "The only reason that I can understand at this point for them to disagree is that the model that we have between them is perhaps missing something. Measuring the universe's expansion takes a little bit more than a radar gun." The first method to measure this growth looks at the so-called cosmic microwave background or CMB, a relic of the universe's first light produced just 380,000 years after the Big Bang. The imprint can be seen across the entire sky, and it was mapped to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this cosmic baby picture, the universe is almost entirely uniform, but hotter and colder patches where matter is more or less dense reveal where baryon acoustic oscillations made it clump. As the universe exploded outward, this soap bubble structure ballooned into the cosmic web, a network of crisscrossing strands along whose intersections galaxies would be born. By studying these ripples with the Planck satellite, cosmologists inferred the amounts of regular matter and dark matter and a value for the cosmological constant or dark energy. Plugging these into the standard model spat out a Hubble constant of roughly 67 kilometers per second per megaparsec. Let's pause on this number for a moment. If a galaxy is at a distance of 1 megaparsec away from us, that means it will retreat from us and us from it at 67 kilometers per second. At 20 megaparsecs, this recession grows to 1,340 kilometers per second and continues to grow exponentially from there onward. If a galaxy is any further than 4,175 megaparsecs away, it will recede from us faster than the speed of light. A second method to find this expansion rate uses pulsating stars called Cepheid variables. These are dying stars with helium gas outer layers that grow and shrink as they absorb and release the star's radiation, making them periodically flicker like distant signal lamps. In 1912, astronomer Henrietta Swan-Leavitt found that the brighter a Cepheid was, the slower it would flicker, enabling astronomers to measure a star's absolute brightness and therefore gauge its distance. It was a landmark discovery that transformed Cepheids into abundant standard candles to measure the universe's immense scale. By stringing observations of pulsating Cepheids together, astronomers can construct cosmic distance ladders, with each rung taking them a step back into the past. It's one of the most accurate means that astronomers have today for measuring distances. To build a distance ladder, astronomers construct the first rung by choosing nearby Cepheids and cross-checking their distance based on pulsating light to that found by geometry. The next rungs are added using Cepheid readings alone. Then, astronomers look at the distances of the stars and supernovas on each rung and compare how much their light has been redshifted, stretched out to longer, redder wavelengths as the universe expands. This gives a precise measurement of the Hubble constant. In 2019, the method was used by Rees and his collaborators, who trained the Hubble Space Telescope on one of the Milky Way's closest neighbors, the Large Magellanic Cloud. Their result was explosive, an impossibly high expansion rate of 74 kilometers.
Esa per megaparsec.
When compared to the Planck measurement, however, Hubble lacked the necessary precision for the crowded regions of space the team was studying, causing some distant Cepheids to blur into neighboring stars. Descending cosmologists had some room left to argue that the result, however shocking, could have come from a measurement error. So when James Webb launched in December 2021, it was poised to either resolve the discrepancy or cement it. At 65 m wide, Webb's mirror is almost 3 times the size of Hubble's, which is just 2.4 m wide. Not only can James Webb detect objects 100 times fainter than Hubble can, but it is also far more sensitive in the infrared spectrum, enabling it to see in a broader range of wavelengths. By comparing Cepheids measured by James Webb in the galaxy NGC 4258 with bright type Ia supernovas, another standard candle because they all burst at the same absolute luminosity in remote galaxies, Rees and his colleagues arrived at a nearly identical result, 73 kilometers per second per megaparsec. Other measurements, including one made by Wendy Friedman with the Hubble Space Telescope on the rapid brightening of the most luminous tip of the branch red giant stars, and another with light bent by the gravity of massive galaxies, came back with respective results of 69.6 and 66.6 kilometers per second per megaparsec. A separate result using the bending of light also gave a value of 73 kilometers per second per megaparsec. Cosmologists were left reeling. According to Ryan Keene, a cosmologist at the University of California, Merced, who has been working to explain the Hubble tension, the CMB temperature is measured at the level of 1% precision and the Cepheid distance ladder measurement is getting close to 1%, so a difference of 7 kilometers per second, even though it's not very much, is very, very unlikely to be a random chance. There is something definite to explain. The new result leaves the answer wide open, splitting cosmologists into factions chasing staggeringly different solutions. Following the Hubble Space Telescope result, an official attempt to resolve the issue at a 2019 conference at the Kavli Institute for Theoretical Physics, KITP, in California only caused more frustration. As the late Vera Rubin, who discovered evidence for dark matter, said at the time, "Nobody wanted to let go of their toy. All of the people involved believed so strongly in their own results and so strongly in the fact that their observations and their measurements were done correctly, it just left people wanting to figure out, how do I explain this? In February 2023, with James Webb and another independent Hubble distance ladder result confirming the Hubble tension, cosmologists are left with three possible explanations: measurement errors, new physics, or some combination of the two. Keane explained that most of the data supports new physics. The simplest and most popular hypothesis is that dark energy behaves differently today than it did in the early universe. If dark energy was strong at one time and then faded away, it would make the universe look smaller when we look back in time to the early universe, making the expansion rate appear faster today. There are other explanations, such as the possibility that there are two kinds of dark energy or that dark matter interacts with light. But these explanations introduce complexities that cosmologists are wary of without further data. Dark energy and dark matter aren't the only mysteries James Webb is helping to solve. When it launched, it was tasked with looking further back in time than any telescope before it. James Webb's revolutionary new imaging technology enabled it to see galaxies formed just 300 million years after the Big Bang. However, while peering at the universe's origins, astronomers found that these primordial galaxies are far more massive and evolved than the standard model predicts. Early galaxies should have been full of young, hot stars forming at breakneck speed, but James Webb showed many of them were bursting with heavy elements from earlier generations of stars and actively building up bulging cores of supermassive black holes. Absolutely. Let's break down this fascinating topic further. The basics of cosmology. 1. The Big Bang and early universe. The universe began about 13.8 billion years ago in a hot, dense state, plasma state. Shortly after the Big Bang, the universe was a hot soup of particles where matter and antimatter annihilated each other, but an imbalance left more matter, leading to the universe we see today. 2. Expansion of the universe. Hubble's law. The universe is expanding, and the speed at which galaxies move away from us is proportional to their distance. This rate is quantified by the Hubble constant. 3. Components of the universe. Ordinary matter makes up about 5% of the universe, dark matter about 25%, invisible and interacts via gravity, and dark energy around 70%, driving the accelerated expansion of the universe. Measuring the expansion rate. 1. Early universe measurements. Cosmic microwave background (CMB), observed as microwave radiation, was produced just 380,000 years after the Big Bang. The Planck satellite mapped the CMB with high precision, providing a Hubble constant of 67 kilometers per second per megaparsec. 2. Current universe measurements. Seed variables and supernovas observe a faster expansion rate, 73 kilometers per second per megaparsec, than predicted by the CMB. The Hubble tension. This mismatch suggests either measurement errors or new physics. James Webb Space Telescope, JWST, capabilities in infrared observations reduce measurement errors, confirming the higher expansion rate observed with seed and supernovas, supporting the existence of the Hubble tension. Potential explanations. 1. Measurement errors. Systematic errors and measurements might cause the discrepancy, but recent instruments like JWST make this less likely. 2. New physics. Variable dark energy or dark matter interactions might affect the expansion rate differently at different epochs. Implications for cosmology. 1. Standard model under threat. The current model, lambda cold dark matter, accurately describes much of the universe but struggles with the Hubble tension. 2. Need for new theories. The persistence of the Hubble tension suggests that our understanding of cosmology might need revision. Early galaxies and James Webb's surprising discoveries. 1. Primordial galaxies. Expected characteristics were young, hot stars forming quickly. JWST observations found massive, evolved galaxies with heavy elements and supermassive black holes much earlier than expected. Conclusion. James Webb's observations have intensified the debate in cosmology by providing precise data that confirms existing discrepancies and reveals unexpected details about early galaxies. Resolving the Hubble tension and understanding these early galaxies might require new physics or a significant revision of the standard cosmological model. The pursuit of these answers is one of the most exciting frontiers in modern astrophysics.